This is a short video to go over the basic information needed to interpret an ECG from a lead 2 recording, which is what we will do in our physiology class. If you've not looked at the video from your textbook that describes the process of setting up the ECG, please do so. It's on Canvas. So this shows you the setup of the recording electrodes for the 12-lead ECG, which is the typical ECG that gives you a perspective of the electrical activity of the heart. And remember, the heart sits in the thoracic cavity with an orientation that is somewhat like this. And a 12-lead ECG is based on the idea that if you put electrodes on the frontal surface of the body and along the fourth and fifth intercostal space towards the from the sternum, the right side of the sternum all the way around to the mid-axillary line, that you will be able to record the electrical activity. You'll get a three-dimensional picture of the electrical activity of the heart. And we'll look in more detail in a couple of slides, but this is just showing you a trace. And remember, the lead 2 is what we typically see in textbooks, and that's what we're going to look at. And the lead 2 shows the current traveling towards this electrode, which is the main axis of ventricle depolarization. And so that is catching, you might say, or seeing that big event of the R wave. All of this hopefully will become more understandable when we look at the next couple of slides. So this first recording method was done by a guy named Eindhoven, who used some math to figure out how to arrange electrodes to get in this triangular form to get a perspective of current traveling this direction, lead 1, current traveling this direction. Sorry, that was lead 2, current traveling this direction, lead 1, and current traveling in this direction, lead 3. And so those are bipolar electrodes, so there's a negative pole and a positive pole, and we'll look at that in a minute. So just to remind you that we are recording difference in potential on the surface of the body. And that means there's a difference in charge between those 2 points where the electrodes sit. And the reason that we can do that is that body solutions contain ions and conduct electricity. So you can think of it as body solutions are like seawater. And that when ions flow across the membrane, cell membrane, through ion channels as a result of events like the action potential, there are currents that travel, so charge moves, and we can put electrodes in different places and look at the difference in charge that arises as a result of that current flow. And the perspective of the ECG is to put those electrodes, for example, here and here. And so we get to see the net effects of positive moving into the cell leaves negative on the outside. And then when the positive moves down the cell or down the heart, that is going to move the positives that were on the surface away in the other direction. So that if you are measuring the difference between spot A and spot B, you will see it appears as if the negatives are at A and the positives are at B. And so you'll measure a difference in potential. So that's the basic idea, and we'll look a little bit more carefully in a moment. So just to let you know, sometimes in the 12 lead ECG, we have this circular axis, and this is considered 0 degrees. 90 degrees is straight down to your feet. 180 is a line parallel to the floor to the right, and 270 is up. And so when we consider, or when ECG expert considers the vectors of current travel through the heart and what we record as voltage signals from the surface of the heart, you will often see degree measurements. So 60 degrees is the main depolarization of the ventricles. That is the kind of the biggest wave of depolarization. And so that will be the biggest wave of current flow that is detected by those electrodes. And any deviation from that axis would be clinically significant. So I wrote these in steps, so we'll go through that. So again, changes in the charge distribution in the extracellular fluid reflect the electrical events of the action potential and can be measured from the extracellular perspective or outside the cell perspective. And for us, we'll be measuring it from 2 places on the surface of the body. If the cardiac, if many cells are firing together, and that's what happens in the heart. Remember, the atria fire together and the ventricles fire together. Then the electrical signals can be recorded from far away. Small signals, so only a few cells, for example, 100 cells in the SA node or the cells in the conducting path, there are too few cells to hear from the surface of the body. So we know that those events are happening based on the timing of the other signals, and we can make interpretations of what's happening, but we cannot see them electrically from the surface of the body. So again, electrodes placed in the frontal plane on the surface of the body in the arrangement of a triangle, Einthoven's triangle, can record the activity of the heart during the cardiac cycle. And I've already told you this, 2 bipolar electrodes called leads 1, 2, and 3, record the potential difference that arises as a result of that ionic current flow across the membrane. Because the lead information can be read separately, it's possible to deduce kind of 3 important different things. I showed you the vector of cardiac muscle depolarization and repolarization, which really means the direction of the average current flow around the heart. For example, the direction of the wave of depolarization in the atria, contractile cells, starts at the SA node, we know that, and then travels in the right atrium towards the apex of the heart, and then spreads to the left atrium with current traveling towards the apex. The lead 2 recording reflects that direction of current flow relative to the lead. So the upward deflection equals depolarization towards that positive electrode, as shown in the picture below, and repolarization in the same vector. Okay, so that's this, and this. Okay, so this is the net kind of electrical vectors, which are the kind of the averages of the current flow, which we see as changes in voltage. Okay, so I'll go through this and then we'll look at the theory in a moment. So right atrium to the apex is number 1, right to left atrium, and also repolarization, and I'm going to write that, and repolarization. Oh, no, that's not correct. I'm not going to write that because that is incorrect. So right to left atrium wave. And then number 3 is from the left bundle branch to the right septum. So it's traveling in a direction that makes the ECG trace from lead 2 look like it's going in the downward direction, okay? It's not traveling directly towards that positive electrode. And then the major electrical activity of the left ventricle, that current flow, 4. And then we'll look at specifically as why does it go up and down in another slide. The theory is in slide 38. And then the S wave appears to go down, and that is due to this depolarization of the ventricle towards the base. And finally, we have the repolarization of the ventricles, and it happens in the same direction of the lead 2 electrode, and so we have that in a positive direction. Okay, so the directions and why we get them in the directions is really a deeper dive. For our class, I want you to know kind of the major electrical events and just the general idea, but not the specific information which I'll describe and is described in slide 38. Okay, so the key, one of the things from these electrodes is we get to see the vector of cardiac muscle current flow and depolarization. Okay, and also the vector of cardiac muscle repolarization. We also get to see when there is no change in electrical activity, so no charge flow during the plateau of the ventricle action potential and during the plateau of the atrial action potential. Okay, so those events are isopotential. The timing of electrical events and their relationship to each other is another really important piece that we get from this ECG of data. For example, the timing of the P wave, which represents atrial depolarization relative to the QRS wave. So that's significant. For example, if the QRS wave is later than expected, that means the PR interval is longer, and there is slow conduction from the atria to the ventricles. And that could mean there's some conduction problems. Also, a P wave that is not followed by a QRS wave indicates a failure, for example, a complete failure or conduction block. So that looking for are the waves present and is their timing as expected from a normal heart function is important when evaluating heart challenges that are being analyzed with an ECG. And last, the magnitude of the current which flows is proportional to the number of synchronously active cells, so the mass of the cardiac tissue. For example, if the R wave is really big for 1,000 cells, and I'm just giving you an example that is not necessarily realistic, if only 500 cells were active during that time, the amplitude of that R wave would be smaller, and that might be clinically significant because it would tell you that some of the ventricle cells are not participating in the electrical event, and maybe there has been cell death or there are other things. So, and the other things could be that the axis of the current flow has shifted, so it's not big in the lead 2 electrode that we're analyzing. It might be bigger in another electrode. So note that the amplitude of the potentials, P, QRS, and T, also depends on the resistance of the tissue that's in the way. And you could go back to the flow model and think about how current flow is affected by resistance. And if the resistance increases, then there will be less current flow. I'm sorry, my phone is ringing, and I am going to stop this video for now, and we'll have the next part of the videos in the next slide,